Today we are going to learn about identifying and fixing overfitting in ML models. You will understand how to detect overfitting, and acquire practical skills to mitigate this issue, thereby enhancing your model's performance.
Welcome to our video on identifying and fixing overfitting in machine learning models. Overfitting is a common pitfall where a model learns not only the underlying pattern but also the noise in the training data, resulting in poor generalization to new, unseen data. In this video, we will explore what overfitting is, why it happens, and how you can detect and mitigate it. By the end of this session, you'll have a toolbox of practical strategies to ensure your models perform well not just on your training data, but also in the real world. Overfitting is a scenario in machine learning where a model learns the training data too well, capturing noise and fluctuations as if they represent the true underlying data distribution. This usually results in a model that performs exceptionally on training data but poorly on new, unseen data. The main symptom of overfitting is a significant discrepancy between training and validation performance: high training accuracy but low validation accuracy. This typically happens because the model has high variance and low bias, meaning it can perfectly adapt to the training data but cannot generalize. To detect overfitting, look for a sharp increase in the error on the validation set, a classic sign that the model is too complex for the given data. There are several common causes of overfitting. A primary cause is using a complex model with too many parameters relative to the amount of training data. Such models tend to fit the noise in the data. Another cause is insufficient training data, which can make it easier for the model to memorize the training set rather than generalize from it. Training for too many epochs can also lead to overfitting, as the model begins to learn intricacies of the noise present in the training data. Lack of regularization, which is a technique to limit model complexity, may also contribute to overfitting. Finally, if the training data is highly variable or noisy without enough instances to capture the true pattern, overfitting is likely to occur. Cross-validation is a powerful technique to detect overfitting by assessing how a model generalizes to an independent dataset. The most common method is k-fold cross-validation, where the dataset is divided into k subsets, and the model is trained and validated k times, each time using a different subset as the validation set and the others for training. This approach helps in reducing the variance associated with random train/test splits and provides a more reliable estimate of the model's performance on unseen data. By averaging the performance metrics across all folds, you can detect overfitting if the model performs significantly better on the training folds compared to the validation folds. Cross-validation is essential to ensure that your model's performance is robust and dependable.
Regularization is a critical technique to prevent overfitting by adding a penalty to more complex models. The two most common forms are L1 and L2 regularization. L1 regularization, or lasso, adds a penalty equal to the absolute value of the magnitude of coefficients. This can lead to sparse models where some coefficients become zero, effectively performing feature selection. L2 regularization, also known as RIG, adds a penalty equivalent to the square of the magnitude of coefficients, leading to smaller but non-zero coefficients. Both techniques help in reducing model complexity and prevent overfitting by discouraging overly complex models. Regularization is particularly useful in linear models where it can significantly impact the model's ability to generalize. Feature selection is a technique used to reduce the number of input variables in a model, thus simplifying the model complexity and improving interpretability. By focusing on the most relevant features, feature selection reduces the risk of overfitting. There are several methods for feature selection, including filtering methods that use statistical tests to select features, and wrapper methods that use a subset of features and evaluate model performance iteratively. By eliminating irrelevant or redundant features, feature selection helps in creating a more robust model that generalizes better to new data. Additionally, simpler models are easier to understand and interpret, making them more valuable in practical applications.
Dropout is an effective technique to prevent overfitting in neural networks. During training, dropout works by randomly setting a fraction of input units to zero at each update, which prevents the network from relying too heavily on any particular set of neurons. This approach forces the network to learn redundant representations, making it more robust. By reducing the network's reliance on any single neuron, dropout encourages the network to develop a more generalized understanding of the data. Dropout is particularly useful in large networks where the risk of overfitting is high. By introducing randomness into the network during training, dropout helps in creating a model that performs better on unseen data. Data augmentation is a technique used to artificially increase the diversity of the training dataset by applying random transformations such as rotation, scaling, and flipping. This method effectively enlarges the training dataset, providing the model with a wider variety of examples to learn from. By exposing the model to varied training instances, data augmentation reduces the likelihood of overfitting, as the model becomes less sensitive to small variations and noise in the data. It encourages the model to learn more generalized patterns. Data augmentation is especially useful in fields like computer vision, where acquiring large amounts of labeled data can be challenging. By augmenting the data, you can improve the model's robustness and its ability to generalize to new, unseen data. Evaluating a model's performance on unseen data is crucial to ensure that it generalizes well beyond the training set. This involves setting aside a separate test set that the model has not been exposed to during training. By evaluating the model on this test set, you can gauge its ability to perform in real-world conditions. It's essential to look for consistent performance across various metrics such as accuracy, precision, recall, and F1 score. A model that performs well on unseen data is more likely to be reliable in practical applications. This evaluation helps in identifying potential overfitting and confirms the model's robustness and generalization capabilities. Consistent performance on unseen data is a hallmark of a well-trained model. In conclusion, overfitting is a significant challenge in machine learning that can hinder the generalization of models to new data. By understanding the symptoms and causes of overfitting, you can take proactive steps to mitigate it. Techniques such as cross-validation, regularization, feature selection, dropout, and data augmentation are powerful tools in your arsenal to prevent overfitting. Evaluating your model's performance on unseen data is crucial to ensure its reliability and effectiveness. We hope this video has equipped you with the knowledge and strategies necessary to address overfitting and enhance your machine learning models. Thank you for joining us, and we encourage you to apply these insights to your projects.